So last time we started to introduce the idea of a BCS ground state where all the electrons are paired up in terms of a Cooper pair electrons. But what the wave function of such a ground state? We have shown clearly a couple lectures ago that the BCS Hamiltonian could be expressed in terms of this Bogoliubov operators, and with the following Hamiltonian, remember we have such a BCS Hamiltonian as we already derive from the 2x2 matrix in a non-Boole basis, that is two electrons from Cooper pairs, and using the Bogoliubov transformations that take us from this C and C dagger operator to this gamma dagger K basis. And in terms of the gamma operators, this Hamiltonian in the BCS state is given by this diagonalized quadratic form of gamma dagger gamma. And as I mentioned, at zero temperature, there's no such a Bogoliubov excitation because this number operator gamma dagger gamma vanishes in the t equals 0 limit, and the ground state energy is given by negative sum over k, capital EK, whereas capital EK is just a Bogoliubov eigenvalues. But at finite temperatures, you get some probability that this Bogoliubov quasi-particles could actually be created. Okay? So the number operators here represents the excitations coming from this Bogoliubov quasi-particle operators. Okay, so this term plays the same role as C dagger KCK in the free electron kinetic energy term that we are familiar with in the very beginning of the Hartree-Fock chapter. So the energy associated with such excitations or Bogoliubov excitations is exactly the same EK that form the say the lower branch of this excitation energy. If you look at this plot, we have E positive and E negative with the same magnitude, which is the square root of this epsilon k squared plus delta squared. So in the BCS ground state, electrons are fully occupied and they're forming these Cooper pairs. But at the finite temperatures, some Cooper pairs may be destroyed by the thermal energies, so they could get excited and jump into this empty states in the Bogoliubov excitations. And this is exactly what happened here, that some of the Cooper pairs are broken and they're coming into the, say, the empty states in the upper branch in that diagram. And as a result, you have finite number of a Bogoliubov quasi-particle. So, but the ground state of such a BCS Hamiltonian does not have any Bogoliubov quasi-particle excitations, because at ground state, this expression value of this gamma dagger gamma is actually 0 in zero temperature limit. Therefore, we could use the concept of the gamma or Bogoliubov operator to define the BCS ground state. The BCS ground state is not a vacuum, but consists of paired electrons into Cooper pair electrons. At the same time, this ground state doesn't have any Bogoliubov excitation. Therefore, we assume that such a wave function, or in terms of Dirac cascade, is written as psi 0, and this psi 0 consists of all the pair up Cooper pair electrons without Bogoliubov excitations, meaning there's no such a Bogoliubov quasi-particles in the ground state. So as a result, if you want to destroy a psi 0 by a Bogoliubov quasi-particle, which we call this Bogoliubov, is the quantized form of the Bogoliubov excitations. And so if we want to destroy this psi 0 by destroying this gamma k, which means that we actually want to destroy, say, a Cooper pair. And in that case, you get 0, because there is no such a gamma dagger gamma in the ground state BCS wave function. Because exactly at zero temperature, there's no such effect coming from this gamma dagger gamma because gamma dagger gamma vanishes. So there are no such terms. Your Hamiltonian is simply just a constant, right? A negative value constant. So therefore, if you want to destroy the phi 0 by applying the gamma dagger operator, you get 0 in the BCS ground state. At the same time, because gamma operators are fermion operators, so you cannot destroy a Cooper pair twice. Okay, meaning whatever your state is, gamma k, actually 0, the same as gamma minus k. So this rule is actually the same as the fermion destruction operator, Ck and C dagger k, that we introduced in the very beginning. So you cannot destroy the Cooper pair twice, and combining these two conditions, you immediately get this BCS ground state wave function as a product of those gamma k, gamma minus k acting on this vacuum, which means that if you expand this gamma k operator in terms of the C and C dagger operators, you'll get such a combinations, right? So in general, there are 4 terms, okay? But we just pick up this finite contributions, which are these 2 terms. The first term is the Ck C dagger k multiplied by this coefficient Uk Vk. And the second term is Vk squared times C dagger minus k C dagger k acting on this vacuum. And you make a product of those 2 particle wave functions, and by summing over all such a state in state k. So that this is sort of the first version of the BCS ground state wave function. So you can immediately see that. So the second term plays a role as creating a Cooper pair. So as you can see that apart from this coefficient Vk squared, you create 2 electrons at the same time, but these 2 electrons are paired up in this k minus k configuration. That spins are antiparallel to each other, and you create such 2 electrons at the same time out of the vacuum. And you make such a product of all such Cooper pair wave functions and summing over all possible momentum state k, and this is exactly this Cooper pair wave function. Yeah, it's a many-body wave function that you simply just make a product of each individual Cooper pair wave functions. But then this, what is the first term? Well, we could rearrange this term by using this fermion anti-commutation rules, and when we do so, you get just a simple, say, a prefactor, UKVK, and the second term is a creation of a Cooper pair wave function. But this wave function is not normalized yet, so we should normalize this so that this normalization is actually 1, and noticing that this UK squared plus VK squared is also normalized. Okay, so if you normalize this psi 0, you get the following normalized BCS wave function, which takes a much simpler form that there's just a coefficient UK as a constant prefactor. The second term is Vk times this Cooper pair operator. Okay, so you could interpret this coefficients as the following, as I mentioned already. UK and Vk are so-called coherence factors in this Bogoliubov transformations. But here, in terms of the BCS wave functions, you should interpret this UK as a probability amplitude not to form a Cooper pair, because this is the term that does not have C dagger k, C dagger minus k, right? But the Vk is the probability amplitude to form a Cooper pair, because this is the amplitude that comes along with the Cooper pair operators. But you can see that this square, the sum of these 2 square, should be normalized to 1. So that comes from this Bogoliubov transformation, which is the unitary transformation. Okay, so this is the standard or normalized BCS wave functions that you should remember. In other words, this BCS wave function is nothing but the product of all those Cooper pair wave functions, across the firm surface, but in the real space, remember, those wave functions are everywhere, so you don't know where they are, but you know that they form Cooper pair in momentum space. Okay, so you take the product of each individual Cooper pair wave functions with the proper coefficient here, and also you add this constant coefficient, which tells you that this probability amplitude indicates that there's no Cooper pair form. So let's just talk about the quasi-particle excitations above the BCS ground state. So we know this BCS ground state wave function as the superposition of two terms. One is the amplitude that the system doesn't form a Cooper pair, plus the coefficient that there is a Cooper pair forming. So what about this quasi-particle excitations at finite temperatures? As I mentioned just a moment ago, that the Hamiltonian in the BCS state is given by this equilibrium of operators, gamma, delta, gamma, and minus a constant, say, ground state energy. So at finite temperatures, some Cooper pairs are broken by the thermal excitation, so they will jump up into the excited state, say the upper band of a equilibrium of excitations, and there's some finite number associated with the equilibriums. But what is the connection between this kind of excitations and the, say, the particle whole pair excitation that we're familiar with in the Hartree-Fock chapter, right? So then we could actually see the correspondence from these following derivations, that we know that in the normal state, at finite temperatures, the electrons near the Fermi surface can form electron hole pair like this, right? But here, in order to excite such an electron hole pair in the BCS state, we need to calculate this kind of processes that electron hole pair operator acting on this psi zero. Because when this one Cooper pair is broken, it releases two electrons, and they could actually jump upwards to the empty states, so that each of these electrons actually come up, leaving behind a hole, two holes. So it's kind of double particle hole excitations, but we need to first break this Cooper pair. But to break the Cooper pair, as I mentioned last time, a minimum energy is required, and this minimum energy is actually 2 delta, because this amount of energy is the minimum energy that allows you to have such excitation processes. Because if you are not at the top of the band or the bottom of the band, then this energy requirement is actually more than 2 delta. Okay, in other words, this 2 delta is the minimum energy to create such a particle excitations and to destroy the Cooper pair. So let's just check this statement here. As I mentioned, we need to check this operation, that a particle hole pair operator acting on the vacuum, BCS vacuum. And so we simply just express the C dagger K, C, K prime in terms of this gamma and gamma dagger, as I mentioned. In the BCS state, everything should be expressed in terms of a gamma, not C and C dagger anymore. So let's just transform the C and C dagger in terms of this gamma and gamma dagger, and this is what we have. So then we just multiply these two terms. You get 4 pieces of the contributions, but only one term survives. All the other terms vanish. And the reason why this term vanish is because precisely this statement that you cannot destroy a Bogoliubov operator if the state is in the BCS state. So there are 4 terms, but the other 3 terms contains at least one gamma operator. So all the other 3 terms do not contribute. So only the dagger terms contribute. But what does that mean? Well, this means that in order to create the particle hole excitations in a normal state, we need to create 2 Bogoliubov quasi-particle operators out of a vacuum, And that is allowed because these two operators are not the same. Because one is gamma dagger k, another is gamma dagger minus k. But we know that in order to create such a Bogoliubov operators, we need to inject the energy of an amount of Ek. Right? But this Ek takes the minimum value right at this Fermi momentum when this epsilon k is actually the same as chemical potential, and therefore this epsilon k hat vanishes if epsilon k is actually epsilon f. So that right at the bottom of the top of the band, this Ek takes value of delta. So you create two Bogoliubovs, which means that you should inject 2 times delta, that amount of energy, into the system. Okay, so this is precisely what it means, that to break a Cooper pair, you need to inject at least 2 delta amount of energy. And to illustrate this in the cartoon picture, this is the Cooper pair electrons, and to actually create, say, 2 particle excitations like this, or to release 2 electrons from this Cooper pair, we need to break this bond between these 2 Cooper pair electrons. And to break this bond, we need to create 2 Bogoliubov quasi-particle operators, which means that we need to have 2 Bogoliubovs. But each of the Bogoliubovs requires amount of energy of delta, and as a result, we need at least 2 delta to release these 2 electrons into this normal state. Okay, and so that is the correspondence between this excitations above the BCS state and electron hole pair excitations that we're familiar with in this Coulomb interacting electron gas. Okay, so once the electrons inside the Cooper pair are released from the Cooper pair and they are, excited states electrons, then they are simply normal electrons. So when the electrons occupy this upper band, so these electrons are just usual electrons. They are no longer bound together by Cooper pairing, so they are simply just normal state electrons. As a result, when the electrons occupy the upper band, all these states that stay in this upper band are simply normal state electrons. But of course, when temperature is not large enough, destroyed all these Cooper pairs, you have a percentage of the electrons that stay in the ground state, BCS ground state, but there is some percentage of electrons are normal electrons. So it's kind of a mixture of the normal electrons and Cooper pair electrons in the system. So that's exactly what we mentioned earlier, that the Bose condensate state at finite temperature shows some percentage of the bosons which are condensed, but the other percentage of these bosons are excited state bosons, which are not condensed. Right? So when we have such a BCS state, this state is precisely bosonic, because say when we pair up these 2 electrons with opposite spin, again in terms of the singlet, and this is called the S-wave pairing. So when that happens, the total spin, of course, 0. So we know that the whole thing, this Cooper pair object, is actually spinless quantity, or does not have spin. And as a result, if you look at this Cooper pair as an object as a whole, and this is nothing but a boson. Okay, so 2 fermions or 2 electrons, when they form Cooper pairs, they are effectively boson. Okay, the whole thing, the Cooper pair, is effectively a boson. And therefore, they satisfy this Bose condensation. So that's another story. But here is how this quasi-particle excitations occurred above the BCS state, and this BCS ground state wave functions that's derived here. So I suppose this is almost the whole pictures of the BCS theory, but of course we could calculate the density of states as a function of the energy across this Fermi level, So you get huge contributions when energy reaches, say, plus or minus delta. So you could check your references for the sensitive states in the BCS state. So let me just make a quick plot. So this is the density states as a function of energy, and this is energy. So this is the normal state, electron density states, and this is the energy associated with the gap, plus minus delta, and you get a shape like this. So if you calculate the density states in the BCS state, which is what inversely proportional to the gradient of your band, the Bogoliubov quasi-particle energy band, and you know what this Ek is, right? So you take the gradient of this Ek with respect to K, and take the inverse. This is the your density states, and then if you plot this, you get these red curves, which shows that the density states as a function of the energy approaches the normal state density states when energy is actually way above delta or way below minus delta. Say, so on two sides of this axis, you recover normal state constant density states, but when this energy approaches plus minus delta as a function of the energy, so this red curve diverges when this energy approaches plus minus delta, which means that when the energy is really close to plus minus delta, where you could actually create many Bogoliubov excitations, then you get huge accumulations of the density states at that energy. So this corresponds to this top and bottom edge of this Bogoliubov energy bands. Okay, so there are many electrons states that are accumulated here in the top of the bottom band and the bottom of the top band. And if your energy is actually way above this delta plus minus delta, then the energy, that amount of external energy suppresses the BCS state so that everything becomes normal metallic state. And your density states, etc. is at a constant value. Okay? So I do not have time to derive this, but you are able to do so. Okay? And this kind of density states profile as function of energy could be checked and observed and has been observed routinely in the lab by the STM. So from the standing tunneling microscope, people could observe such a kind of the density states profile when they consider, say, the NS junctions. So this is the a junction made of normal metal and the superconductors. So the STM can actually probe the tunneling between the normal state to the superconducting state and vice versa, and the signal is actually proportional to the density states. And this is precisely what they see. I guess that's probably the end of this BCS theory, and I hope you get the complete pictures of what is going on when electrons form Cooper pairs in metals. Okay, so any questions? Yes?
老师说Cooper 它是bosonic 磁层，但是它却像 fermion 一样持有两个结，所以不能够摧毁两次。就是我不懂为什么，如果它是 bosonic 的话，它却不能够被 destroy 两次。为什么好像这样光子好像就可以
Well, but if you look at this BCS Hamiltonian, which is in terms of fermionic operators, right? So as you can see from here, it's very clear that at ground state, there's no such Bogoliubov quasi-particle operators anymore, where gamma is a fermionic operator. So there's no such occupation for gamma here. So if you wish, you could very clearly see the number of gammas is actually 0. When the number of gamma is 0 and you destroy this n gamma equals 0 state by a gamma k, of course, you get 0. Because remember, we have this single occupied state and empty states, and as a two possible fermion occupations, and you could create an electron out of a vacuum, and then when you create that electron, you get single occupied state, but you cannot create the same electron state twice. Okay, but if you're already in the vacuum state, and you cannot destroy a vacuum. And this BCS ground state is the vacuum of a Bogoliubov quasi-particle operator. It is a vacuum just of such a gamma operator. It's not a vacuum of a Cooper pair. It is made of Cooper pairs, but it is a vacuum of the gamma. Right? So if this is a vacuum of gamma, you cannot destroy gamma if there's no gamma. Right? So the bosonic nature in the BCS state is not clearly shown here. Okay? So we need to make further derivations to see the connection between the boson and the Cooper pair. But you can see very clearly from the fermionic picture that if you don't have any Bogoliubov quasi-particles, you cannot destroy it. You cannot destroy the nothing. Okay, is that clear? Good questions. Let's take a short break. When we come back, we should come to the final chapter, which is the magnetic properties of solids. So for the BCS state, please refer to all the details in the Flansburghs and other references. I'm not sure we have enough time to cover all these magnetic properties of solids, but let's try. So in the remaining couple of minutes, I should just take an overview of a magnetism in solid state physics that you already learned, but you may not know precisely what they mean. In solid state, we have several magnetic interactions or magnetic states that you are familiar with, such as paramagnetic or paramagnet, and including a polyparamagnet. And we have ferromagnetic properties or some ferromagnets, and we have anti-ferromagnetism. And all these solid state materials shows diamagnetism. Okay, so all these magnetic properties of solids come from Hahn rule coupling, which I leave this to you as not a homework, but just for review. So you should have known this Hahn's rule. There are two Hahn's rules, Hahn's first rule and Hahn's second rule, which allows you to actually fill up all the electrons into this corresponding, say, configurations, say, electronic configurations, this SP, DF, and so on and so forth. And what is the rules that you need to fill the electrons into that particular orbitals? They should follow Hahn's rules. So depending on the Hahn's rule, so there are some leftover spins in some certain orbitals that do not cancel their spin angular momentums, and as a result, there are some residual magnetic moments in some particular orbitals in solid states, and that's the origin of all these magnetic properties. And also, those electron spins may actually interact with the other electron spins if they have some unpaired electron spins in the orbitals, and so they form a particular arrangements of this ferromagnetic or anti-ferromagnetic spin orientations, and all solid states show some degrees of diamagnetic properties, where in the states, it repels this external magnetic field, just like BCS states, which is a perfect diamagnet, but non-BCS states or non-superconducting states shows some degrees of diamagnetic properties. So I leave this to you for review. So let's just look at this first example, the paramagnet. So those states appear in this free atoms with odd number of electrons or partially filled inner shells. And second, all the metals in the metallic state, not in the superconducting state, they show paramagnetic properties. So this magnetic moment in that materials, we know that there's a G factor. The G factor follow this quantum mechanics formula, which I don't have time to derive. You could check your solid state 1. The G factor is the factor in this magnetic moment of your material. For example, if you have the spin 1/2 states, you know that this states splits in the presence of the field into plus 1/2 and minus 1/2 states, and the Zeeman energy is given by minus magnetic moment mu dotted the external field B, right? And so in quantum mechanics, you know that this is given by this quantum number mj, where mj is just a quantum number associated with this total angular momentum j, and the g is the g factor, and mu b is the Bohr magneton, and so Zeeman energy is actually quantized in terms of g times mu b times b. So suppose I have orbital angular momentum, just a spin angular momentum. So we have only two possible states, plus minus 1/2 h bar. Then you could actually derive such an occupation for spin up and spin down state. So based on their Boltzmann weight, they have different occupations. As a result, if you are in the finite temperature regime and you have magnetizations. Okay, so this is familiar to you because the end up state, the number of spin up states and down is different value because they have different Boltzmann weight. And the denominator is just a partition function. If we have only two possible states from the spin 1/2 electron, as a result, the finite temperature number of spins, electrons stay in the up spin, and in the down spin state is different. As a result, you get the net magnetization because the difference between spin up electrons number and spin down electron number. So as a result, you can define magnetic susceptibility, which is the ratio between the magnetization to the external field. So you could take a Taylor expansion, and this gives you 1/T behavior, which we call the Curie law, which means that for a system with magnetic moment mu, and in high temperature limit, the magnetic susceptibility, which is the derivative of magnetization with respect to this field, goes like 1/T with some proper universal coefficient, which we call the Curie coefficient C, and this is called Curie law, which means that even though there are some net magnetic moments in the paramagnetic state, but those moments are free and they're disordered and they are random. So we don't have an ordered magnetic order state, but at finite temperatures, in the presence of the field, a small magnetic field, the magnetization goes like a hyperbolic tangent function, this function of mu b over kbt, and the spin susceptibility goes like 1/T. Okay, so and this applies to almost all metals or free atoms with odd number of electrons or partially filled inner shells. Okay, so this is really straightforward coming from your solid state 1. But there is a polyparamagnet. At low temperatures for metals, we have such energy bands structures in the presence of the field. You know that the field, magnetic field, say favors one spin species out of the others depending on the orientation of the external field. So suppose this left band corresponds to spin up states, and on the right this is spin down states. So this is mu b and this is mu b. So at zero temperature in the presence of field, the Zeeman energy actually shifts the spin down state upwards, but the spin up state downwards, so that these two bands are not the same anymore. So they differ by 2 mu b energy shift, but the chemical potential is actually the same. As a result, there are more spin up electrons than spin down electrons. But of course, depending on your field directions, so this spin up state and spin down state could be interchanged. So suppose this is the case, then the end up is actually could be estimated from the free electron model in the presence of the external field, and this is given by the average electron number plus or minus the Zeeman energy. For spin up states, and up is the average value plus 1/2 of the mu b times density of states at the Fermi level. For n down, you integrate over the energy windows where you have the finite density of states, which is the average density of states minus 1/2 mu b times the epsilon f. So as a result, you have the net magnetic moment again, but this is at zero temperature limit, which is a constant. Tf is the Fermi temperature. So you take the ratio between n and b, you get a constant spin susceptibility. Okay, so this is called magnetic susceptibility, which is a measure how easy or how hard that you change your magnetization in the presence of external field. If this is a large value, then which means that the response to the field of this magnetization is large, and if this chi is small, which means that the response to external field is small. So for all metals in the zero temperature limit, in the presence of field, you get the Pauli paramagnetic properties, which means that the spin susceptibility, zero temperature limit, is a constant which depends only on the density of states at Fermi level. Okay, it's called Pauli paramagnet, but at higher temperature, the chi of a paramagnet follows Curie law. Okay, so I guess that should be enough for today. And on Wednesday, we will, apart from the other magnetic states, namely the ferro and the antiferro, we will introduce the quantum mechanical treatment of a ferro and antiferro states. And then we end all these topics for this semester. And okay, so please read your Advanced Solid State 1 and also Flansburgh for details.